Hi, I'm Mrs. Jamie Thompson. I'm a 4th grade teacher at McClelland Elementary, and we are having Mr. Crosslin in here with us today, and our lesson is called Heat Moves.
Hey, thanks for that introduction. Today we're going to be talking about heat moves, how heat moves through things. And that's a good thing because it's starting to get cold outside. And I'm glad it's warm in here and it's cold out there. So the first thing I hope we're going to learn today is that heat moves in which direction? What do you think? Does heat move from hot, then it gets hotter? Or does it go from cold, colder? Or does it go from hot to cold? Or does it go from cold to hot? If something was hot, like let's say a cup of hot chocolate, right? Oh, everybody wants a cup of hot chocolate. Here's a cup of hot chocolate with some nice heat. If you came back in 20 minutes, would it be the same temperature? Would it be more or less? How does heat move from hot to what? What do you think, class? To
cold.
Cold. Yeah.
Cold.
Heat moves from hot to cool or cold, and that's kind of interesting. So if you take let's say you take a baked potato out of the oven. Oh! How's that baked potato? It's kind of hot. And you set it down, and you come back in 20 minutes, and you pick it up, and it's probably
Cold or cool.
Cooler, maybe a little warm. Wouldn't it be weird if you took a baked potato out of the oven and you sat it down, you came back in a minute and it was hotter, you came back in a few minutes, it was hotter, you came back in 5 minutes and it was on fire? That'd be weird. Luckily, the world doesn't work that way. Heat moves from hot to cool. They don't go the other way. Here's something else I want us to explore today. We're going to call this heat energy. Heat energy. Another name for it is thermal. Heat energy. If I had a small, you might want to draw this too. If I had a small little cup, and this was, let's say that was 90 degrees Fahrenheit, and I had a large cup, let's say that was 90 degrees Fahrenheit, which one would have more heat energy, A or B? Which one do you think, class?
B.
B. This one would have more heat energy even though they're at the same temperature because there's more matter there. Think of it this way. Have you guys ever had a bowl of soup?
Yeah.
And the bowl is a bowl of soup, and the bowl is really warm, right? And hot. But you take a spoon, right? And what do you do when you have what do you do to that spoon, that hot soup, before you drink it? What do? You blow on it, right? And that cools it. What if you blew on the bowl? If you blew on the bowl or the spoon, which one would get cooler first? The spoon, because it has less heat energy. So those are two things we're going to investigate. Heat moves from hot to cool, and heat energy, the more matter, the more heat energy. Okay, so the next thing I want us to talk about is kind of interesting, and I kind of love it. We're going to make 3 different drawings because I want to introduce to you 3 ways that heat can move through 3 different things. So check it out. So somewhere on your paper, we're going to divide your paper into 3 parts. We're going to talk about this. We're going to talk about, maybe you've heard this word before, conduction. Everybody say conduction.
Conduction.
That's when heat goes through a solid. Okay? And then we're going to talk about something called, check this out, convection, and that's when heat goes through a liquid or a, what do you think? Gas. And then we're going to talk about another type of heat called radiation. You guys are well prepared. Radiation. And that's when heat goes through empty stuff and strikes a solid. So, we have, repeat after me, conduction, which is for a solid, convection, heat moves through a gas or a liquid, and radiation. It goes through empty space and it strikes a solid. Here's my drawing on this. Check it out. And I want you to make the same drawing. Let's say we have a piece of metal, solid piece of metal, right? And we heat it up on this end. You know, I should probably use a red marker to show you heat. Why not? So we're going to heat it up on this end right here. Ready? Heat, add heat to it, add heat to it. The particles inside of here will start to send that heat on down it. This is kind of cool. This side will be really hot. What will this side be down here? It'll be cool, but the heat's coming. So look how, this is our model of heat particles starting from a hot side going to a cool side. Got it? Let me give you a chance to draw that.
Mr. Crosslin, Jimmy's good too. You get.
So that was conduction through a solid. Check this out. Here, let's move over here to, you've probably seen something like this before. We have a large pan, right, with a handle. And remember I said convection is through a liquid. We'll put some water in here. And a gas. So we have air up here, and we have water down here. So this is what happens. When you heat up the bottom of this, let's add heat right here. The heat goes, these particles start to move. And since they're in a liquid, they take the shape of the container. They start to move, and they move faster and faster, and some of them start to boil and escape as gas. And so we start seeing particles coming up, and we call this convection. What do we call it?
Convection.
And sometimes we call them convection currents. Has anybody ever been driving down the road on a hot day and the road looks like it's all wavy in front of them? Yeah, that's the heat heating up the road and the road heating up the air. Air is a gas. So here is convection currents both in water and in gas. I've been heating up for our experiment some water on this electric stove that's converting electricity to conduction, and maybe you can see what's coming up out of this hot water. Do you see the convection currents coming up? Does anybody see that?
Yes.
Very good. All right, so we've talked about conduction through a solid, convection through a liquid or a gas, and the last one is probably your favorite, radiation. And the best way to explain radiation is when energy, let's say from like the sun, when energy from the sun, and this is not the scale, but energy, ding, 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 goes through empty space, and it goes through our atmosphere and hits the earth. And when it hits it, it strikes the earth and it gets hot. So radiation goes through empty space. It doesn't do anything until it strikes a solid or a liquid and it starts to get hot. So we have conduction, convection, radiation. So let's see what that looks like if we use a model with some students and some heat particles. All right, so I got some students here. You guys, we're going to show conduction. Conduction is, right now you're a solid. That's why you're all elbow to elbow, scoot in solid. So you're one solid piece. You have a definite shape. You have a definite volume and definite mass. These are your heat particles. So I'm going to start to vibrate and heat you. Heat, 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 and you can feel it going down and going down. The next person feels it. Start sending your heat particle down. Your heat particle. Give it to the next person. Give it to the next person. Here you go. And send yours down. Send yours down. Send yours down. Send them down. Send them down. Send them down. Send them down. Now, slow down. Now we're starting to cool down. The heat particles are coming back. Heat particles are coming back because we're cold. This way. Heat particles are coming back. Heat particles are coming back. Hold that one. 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 That was conduction, heat going through a solid, cooling down, and coming back. Okay, let me show you a different model. This model is if you are convection currents. So convection means that we're a liquid. So this is our container. Everybody get in the container, and you're just having a good life. You're a liquid. You're just moving around slow. You're vibrating. You're moving around slow. You might bounce into somebody. Oh, excuse me, and bounce away. Oh, excuse me. Oh, excuse me. But now we're going to turn up the temperature. When I turn up the temperature, the heat, you're going to vibrate more. Here comes the heat. Let's go. Boom. Oh, 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 boom, boom. Oh, excuse me. Let's turn up the heat even more. Boom. Oh, turn down the heat. Okay, we're moving slow. We're moving slow through convection currents. Turn up the heat. Here we go. Turn up the heat. Oh, boom, 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 boom. It is so hot now that we're going to turn into a gas, and I'm out of here. And so is Barry. We're both out of here. Okay. Oh, slow down, slow down. Now, the two gas molecules, we're so lonely that we're starting to get cold now. Give me let me see your molecule. Let's get back. Oh, we condense. We turn back to a liquid. Thanks, guys. And we're moving around again, moving around again. So convection is when the particles move. The more heat, the more they move. They can even turn into a gas. So here comes our particles right at the camera. Bring them this way, everybody. And okay, so the last thing that we're talking about is radiation. And if you remember from your drawing, radiation is when heat comes like from the sun through empty space, through the air, and strikes either a solid or a liquid, like the earth. So in this case, they're going to be the sun. Let me see your heat particles. And I'm going to be the earth. And I think I'm going to be heated up by radiation. Are you guys ready?
Yes!
Oh, brother. Here we go. On the count of three, say radiation and launch your heat particles at me. And let's see if I get a little hot. 1, 2, 3.
Radiation!
I mean, hot, 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 hot. Good job. You guys loved doing that, didn't you? Okay, I can see that we're ready to do some heat moving. So our solid aluminum pan is heated up by conduction, and the liquid water inside of it is boiling, and it's heating up by convection, and it's actually coming up into the atmosphere. So let's take this hot water and see if we can learn a little bit more about conduction. Okay, we're going to do an investigation to see which material is a better heat conductor. Conductor lets heat go through it. What's the opposite of a conductor? Insulator. So I have two different spoons here, and they're the same size, same shape. One of them is made out of metal, and one's out of plastic. Which one do you think heat will go through? Which one is a better conductor, do you think? What do you think?
The metal.
Metal? So some people think metal? Does anybody think plastic? Okay, you think? Okay. Well, here's the thing that we're going to do. We're going to see which is better. And here's how we're going to do this. So first we're going to start with 120 cubic centimeters of cool water. So I'm going to pour this up, and I'll go over this again. Here's 120 cubic centimeters of cool water. Now I know it's cool because we have a thermometer here. Now this thermometer is sharp, so don't poke anybody with it. This is a turkey thermometer. I don't see any turkeys here.
No.
Okay. So I'm going to put that in there, and it says it is, when I put it down there and I let it go around, it says it's between 60 and 80. So between 60 and 80, what do you think the temperature is between 60 and 80? 70 what? 70 bananas?
75 degrees Fahrenheit.
70 degrees Fahrenheit. Okay, so that's cool. Now, we have some butter here. And we're going to use a little bit of butter, just a little bit, all right? Too much butter and it's going to not work as well. So here's just a little bit of butter. See how little that is? Okay? And a bead. I'm going to stick it right here. See, butter at 70 degrees in this room is a solid. And then I'm going to set this right in here. Okay? I'm going to take my plastic spoon. And do you think I should put a big glob of butter on this one?
No. The same amount.
Thank you. For a fair test, we should have the same amount, and that's real important to put the same amount of butter. And so we're going to just put a little bit of butter, and then I'm going to, thank you, stick in. You think we should put one on the front and one on the back? Or
No.
we want a fair test, don't we?
Yeah.
So stick it on there. And now, I'm going to put this in the cool water, okay? And then I'm not going to touch these. I'm going to leave them right here. Now, since that's cold water, we're probably not getting much heat going up the stem of that spoon, are we?
No.
No. But what would happen if I added hot water? See, through conduction, the water's going to be heat, and it's going to start heating up the spoon. When it goes up the 2 spoons, what is it going to do to the butter, do you think?
It will melt. It's going to be a solid.
It's a solid now, and if it gets hot, it'll turn
liquid.
What will happen to the bead?
It would
It will
fall.
fall. So I want you to, we're going to read about this, you're going to take notes about it, and we're going to time it. We're going to put a clock up on the board in just a moment. I'm going to bring you some hot water. I'm going to pour it in. We're going to do that in just a moment, and we're going to see what time, click, start our watch. Which one do you think is going to fall first?
Metal.
If you think metal is a better conductor, it's going to go up here, and that might be, I don't know, it might be a minute, it might be 2 minutes, maybe.
Plastic.
And then plastic, it might be 1 minute, 2 minutes. We're going to time which one. You want to try that? Well, let's see what it looks like with hot water. Okay, so here's some of the very, very hot water. And we're going to add, I'm going to come by and add the hot water to this. And when I add the hot water to this, the temperature, you tell me when I add this what the temperature is. It is 70 now, but when I add it, what is it doing?
It's changing.
It's changing. In fact, it's now what?
Hot.
It is hot. About 120 degrees Fahrenheit.
Whoa.
So let's get everything ready. All right, so I see you've got your cup set up. You should take the temperature right now. So you have cool water, and you have a plastic and a metal spoon, and we're ready to add the heat. Look in your science journal and your science workbook on page 144. And what we're going to do is we're going to start a timer. And when I add hot water to your cup, you write down the time. You got that? Are you ready? Okay, we'll let the conduction begin. Okay, right, 11:03, and I'm adding hot water. Check what happens to the thermometer.
It's going up. I see it.
Very good. Check it out.
I see it going all the way up to the hundreds.
100 and what? Don't move it, don't move it, don't move it. It'll mess up a little bit.
It's
Wow.
it's
100 and what?
it's 100 degrees Fahrenheit or 40 degrees Celsius.
Wow. Here we go, 11:04. Add the hot. What did the temperature go up to? What did it go up to?
80.
What is it going up to?
85. 100. That's not all. 101. 102. 103. 104. 105. 105. No.
All right, let's
105.
check the time. Ed, what's going on?
The silverware is starting to fall, like it was up there, now it's coming down
And so why is it starting to fall?
because the butter is starting to get.
Because of the heat.
Because the heat is making it like come down.
And so the butter is starting to melt, right?
Yes, because of the heat.
Okay.
I'm surprised that the
What about the plastic one?
The plastic was
one is not
staying.
doing nothing. It's just staying.
Okay.
You can see a little
And you can't?
Well, not really. The plastic one is.
Got it.
Yeah, this
And-
one's not melting,
Heat is
but
making the
this one is.
the bead
Mm-hmm.
on the silver
It's making it melt.
Yeah.
Because it's got heat going up through
Yeah.
so it's a better conductor, huh?
You can kind of see it a little.
This one is just staying. It's a level of
kind of see. The bead is starting to slip. It's pretty slippery.
It is slipping. Here it goes.
It's gonna fall pretty soon. Come on, bead. You can do it. You can do it. It doesn't have a brain. Don't give up. It's like
I
on
can
a
see it
silver slide.
moving.
Can you see it move?
It's like it's going on a slower than a snail slide.
So as the heat goes, it'll finally fall on in there, right?
Yep. You just have to be patient. All of that heat. My voice can make the water move.
I noticed that.
Yeah.
All right.
That's
so,
another sight.
It
nice. Okay. Good job. Okay, you can see that depending on how much butter you put on them, we got different rates that they'll fall. Good job. Is yours starting to melt at all?
No, not really.
I think it is. It's a little bit. All right.
All right, we're going to end our lesson. So Franklin, tell me 2 things that you learned today.
I learned that the plastic spoon is a insulator and the metal one is a conductor.
Now, how did you know that?
Because the metal one, the heat from the water traveled up and it made the butter melt, and then the bead fell down, and the plastic is still on.
Thank you.